Oh wait, where are the problems? Dude, I don't have the problems. Okay, there we go. Find the next palindrome. 00 to 23 and 00 to 59. Oh, dude. Okay. I should really set this up. How do you do two-string? I forgot C++ syntax, dude. That's OCaml. Dude, how do you convert an int to a string? Wait, other way around. Oh. Oh, you got that. All right. So what we're doing today, I just started. stream without telling you what's going on. But this is my friend, and we're doing a practice round of Blitz Cup. Yeah. We just did problem A. Now it's problem B. That was actually super fast. That was like engine speed. Okay. Yeah, so we're doing a speed coding thing, where each of the problems is worth a certain amount. So A was worth 2, B was worth 3. He submitted twice? What? I don't get that. Maybe he wrote code straight on that. Okay, never mind. Maybe I wasn't that fast. All right. Next problem. We just go for 40 minutes, by the way. So whoever solves the most number of problems in 40 minutes wins. Should probably have my notebook open in case I need to write something down. What? Excuse me? Oh, this is so stupid. So for each cell, you need to figure out how many. Wait, how big is this grid? Yada yada. Oh Jesus. Okay. Okay. Wait, what? What does this input mean? N and K. 9 gorillas, all of height 1. Oh, okay. Alright, so we basically need to find the sum of, like, the maximal sum of this. And it'll be like the ones in the middle are always the best ones, so for each cell, subsquares of length k with a, just have to figure it out. How big is, oh, the sum of n times m is not big. Okay, so we just go through them. Dude, I need to read constraints, man. I need to read constraints. It's not good. Yeah, I think that just needs to be done at some point. Okay. So now we need to go through them all, and what do we need to do? We just need to go through all the cells in order of height, basically. Or we can just create the whole grid, honestly. So for each gorilla, for each cell, we have to figure out how many different, like, ones of length k. So the top can be at I minus, dude, I'm so bad at these off-by lines. The top can be at I minus k plus 1. To I. But also the top has to be max between this and n minus 1 minus k plus 1. And this is min between I n minus 1 minus k plus 1 is here. And this is, dude. think. And then like I do this, which is just the same but for j, and then I do max minus min plus 1 times max 2 minus min 2 plus 1. Finally, this is just this. J minus k plus 1, j m minus 1. Let me just submit before I even test. Okay, that's wrong. What? Am I even inputting stuff right? Tests. And then 3, 4, 2, 9. This is W. This is W. This is W. Come on. Come on. Let's go. These ones are really annoying, man. I mean, you can't see what I'm doing right now because I don't have my screen shared, but I've got this, like, you know, this grid drawn, and I'm doing some. I'm optimizing this to the extent that I'm like copying this so that when I create the new problem on D, I can then paste it straight in without having to copy it. This is like immense optimizations. Okay. Next problem. I don't even know how long it's been, but I think it's been half of it. Here we go. Problem D. Wait, it's not really loading though. I'm gonna be real with you guys. There we go. And heaps. The ith heap has hi stones. You want to change the number of stones in the heap by performing the following process once. You go through the heaps from the third heap to the nth heap. Let I be the number of the current heap. You can choose a number. Move D with triple D being at most hi, and you move D stones to the next one and 2D stones, D stones to the previous one and 2D stones to the one before that. Okay. Some heaps may become empty, but they still count as heaps. Sure. What is the maximum number of stones in the smallest heaps after the process? So I want to even these out by maximizing the number in the smallest heap at the end of this process. All right, so let's look at an example. I've got 1, 2, 10, 100. What am I doing here? I start with the 10 and then the 100, and then I can move things twice, right? So this is going to be some kind of DP, right? If I know how many stones I can have in the... Wait, how big are these numbers? Oh, they're kind of massive. Never mind. It's not DP. It's not that DP at least. So the 10, I'm going to move back to the 1 and the 2. Wait, how do I move these again? So I move D to the previous one and 2D to the one before that. So however many I want to move, I'm going to move double that to the one before, but then that's all it's going to be, right? So I just need to binary search this. And then you only move to the one before as much as is necessary. Wait, no. Because imagine you have like 1 to 110, then you might need to move a lot from the 100 backwards just so you can get the 2 up as well, not just the 1. What? I don't get this actually. I don't know what to do here. 100, 100, 101. You can't do anything here. 1, 2, 10, 100. So it's 7 is the answer here. So you can get to 7. That means you have to move 6 back in the first move to 1. And that'll move 3 to 2. Wait, no, you need 5 to go to 2 at least. Wait, why is it 7? Why is it 7? Oh, other way around. Sorry. The problem is 1, 2, 10, 100, not the other way around. So why is it 7 though? Oh, it's because, yeah, you need to move something back to the 1 and only the 10 can reach. So you actually just move like as many as you can back. So you move 6 back and 3 back, yeah. And the 100 helps you out. But then, what if you did have this case? 1 to 110. How would you solve that? Because the 100 can feed the 1 and lift it up to as high as you need it to go. And obviously, you can't do any operations on the 1 after that, so you need to put the 1 above where you need to be. But then the 2, you might not be able to add stuff to anymore. So the fact that you're adding more to the 1 before is actually makes things harder. Because what if now like the 10 didn't have enough to give the 2 that much? Let's say you wanted to get to 7 and you had 7 to 107, right? If you want to get to 7, then you have to not touch the last one. But then yeah, you need to move something from the 100 to the 2 to get it above 7. So how am I solving this problem? I need to what? Okay, let me think through a different example. Because this binary search point kind of works, but it also doesn't give you the. It doesn't let you. It doesn't make it obvious what moves you're going to make because of what I just said. Okay, let's try this. 5, 1, 1, 8. Yeah, so we can't really fix this. It's just going to be 1. All right, that's not very interesting. 1, 2, 3, 4, 5, 6. That's interesting. So I'm moving 2 and 1 back. To make it 3, 3. Then we 3, 3, 0, right? Then we have the 4. Wait, what if we work from the back? So if imagine we want to keep we want to keep 3 in everything, right? Oh, we work from the back, bro. Bro. We work from the back. It's like 1 word, and it just solves the problem. That's kind of cool. It's quite cool. I haven't even fully thought this through, but I'm pretty sure that just solves the problem. All right, so we binary search. Let's see. 10 to the 9, right? So 0 to 10 to the 9. Then making everything at least 0 is obviously possible. And infinity, which is, let me just make these all on one, just to make life so much easier. Right? And that's like the sum of, I mean, I guess it has to just be 1 even. That's impossible. So now I go through all of them, and then I say if the value, the current one, oh, he solved it. You got it. Okay. That was quite a cool problem. It took me too long to figure out how to do it. Yeah, nice. Okay, we got E coming up. This is a close one. Okay, so I think I'm behind by like 1 point. So I need to solve E. I need to solve E. Oh, Jesus. Oh, okay, fine. We can move. We have a robot that can move. We want to modify the operations. Okay. This is actually not Not that bad, but it's like kind of effort to code, man. So I've got n and then just n characters. So let me just do this. Wait. Let me just do this. If si equals up, dx equals dy equals plus 1. If si equals down, dy equals minus 1. If si equals left, dx equals minus 1. If si equals left, dx plus 1. Don't need this. So I need to go through these now. Calculate sums. Wait, why do I have this open? That's just in the way. I need to calculate sums. All the possible start positions, and now we should find the closest possible end position with finance. So the point of this is I just have to check I need to sum it up to the start, and then -1 in theory, but like I don't need that because of the indexing, plus sx at the whole thing minus sx at the, so end is like, imagine if start was 2, end was 4. N equals 6, so I'll get like the whole sum plus the sum of 2, and then I also need to subtract this sum, right? That's n plus 1. Oh, jeez. I said 4 for this? Wrong answer on test 4, okay. So this seems correct. So start -1 is definitely possible, right? It's definitely impossible because like you're negative. Start and n is definitely. Oh, it's done. All right, that's it. That's GG's, dude. What? Okay, that was a close one. Well played. Yeah. There's a bug somewhere in here, but I like this was the idea. Let me try and figure out what the bug is real quick, but otherwise that's it. So we go through all possible start points for the change, and then we find the first. We have to find the first position where we can end the change and it'll still work, right? And that's the previous position. Obviously, you can't end the change before you start it, but you might be able to end the change, on wherever you started the change, and then post end, we'll just check at the end. So this is fine. We take the middle. These are the extra positions we have to play with. The current totals we have are the ones up to and excluding start, plus the whole thing minus, so the ones after end, basically. And that's the whole thing minus this. So if end was n minus 1, this would just be empty, which makes sense. Last end is, yeah, okay. This won't go out of range. Same for y. And then, oh, no way. It's parity, dude. It's parity. Like, we might have enough positions to do this, but we also need the parity to do it as well. Yeah, okay. Yeah, that makes sense. I just need an extra check in here to check that, like, the parity of x plus y was the parity of the whole thing. Okay, makes sense. Yeah, what happens? Like, this is super fast paced, and you just don't have time to think through. You think of a solution, and then you just pace it. Yeah. So GG's to Will. Let me see if I can get him on a call, actually, real quick. Quick call to see if we can discuss the problems. I mean, they weren't insanely difficult, but it would be cool to do that. I need to figure out how to set up a Google Meet, though, which I should have done beforehand. This kind of started super fast. Okay, here we go. This is actually super speed based. It's insane how certain different strategies pay off in this compared to regular contests. So FYI, while I'm trying to set this thing up, we'll see if I can multitask and talk to you about something completely different while I do that. But I did the first round of the competition, the actual competition. This is a friendly, but I did the first round a couple of days ago and somehow won. So round 2 is tomorrow against another IGM. So I mean, I guess I've done it once before, but again, I expect to lose this one. But we'll see how it goes. So about 4 p.m. tomorrow should be when that happens. Oh, wait. I just realized I haven't configured the audio for this call to work. Yeah, I should have thought of that. Like, you guys aren't gonna get the audio from this call. Yeah, I don't think this is gonna work. I guess we'll try it, but I just don't think we'll be able to hear him actually. Yeah, I should have set this up. Hello?
Really? Why not?
Hello?
Oh, yeah, put the stream open.
Oh yeah, I can hear you. Um, I just realized people
Hello?
other hello?
Oh, yeah, I can't tell if I can hear you through the stream or Google Meets.
Oh, okay.
I think you're muted on. Yeah, I can only hear you on stream.
All right. How do I? All right, I should have thought of this. This is kind of stupid. Okay, you should probably be able to hear me now, actually.
Oh, okay, yeah, I can hear.
But I don't know if the stream can hear you. That's the thing. Do you?
Let's see.
Can you tell if they can hear you? Because I'm not also listening to the stream. If you get the stream open, I can also get the stream open.
Yeah, I got the stream open.
Okay.
I'm a bit delayed, so I should know. I know they should be hear me and you.
Oh, really? Okay. All right.
Okay, that's good.
All right. That's nice. Wait, why is someone else trying to join the call?
Wait, really?
I sent it.
Oh, wait, you can see the URL. That's why.
I sent it straight to you, I think. But yeah, you can see URL. Fair enough. Okay. I'll just full screen. Yeah. That was kind of fun. GG's.
GG, yeah.
I mean, we got through 5 problems basically. I mean, I saw you submitting E as well, so I assume you had something.
I mean, I have my strategy is to submit and then compile and test it. So I'm probably further from solving it than ever.
Yeah. So for the problems. So yeah, I mean, we had 5 of them. We can just go through them if you want to talk about them.
Sure, yeah. But you that for the beginning, because I know I confirmed it myself, but then didn't check.
I mean, actually, I didn't confirm that I was ready for the time, but it started anyway. Like, I mean, I was kind of ready, but I hadn't confirmed it, and I assumed it would cancel, and I was about to send a new one. But no, I wasn't like. I mean, I started like 10 seconds late, I think. But yeah.
Okay. It's a pretty implementation problem, so it's probably.
Yeah. Yeah, like it wasn't a big deal. I mean,
all right.
I don't know if it changed anything. Yeah,
I couldn't figure out how to pass a string in C++, to be honest.
Yeah, I mean, I was really close on A actually. I think I copied it into my clipboard, and then I saw you solved it. But it was kind of longer to implement than
Yeah.
Obviously,
that's to be on B. I finished debugging, and then you got and you got. I saw you submit, so you got accepted.
Oh yeah. So I mean, I can try like sharing a whiteboard or something, and we can talk about that if you want.
Sure.
All right.
We got some harder problems, but
Yeah. I mean, what are the difficulties again? They start at 1,000 and then 1,200, 1,400, right?
yeah, it goes up in 200 until 2,200, I think.
Until 22. Yeah, I mean, in my actual round yesterday, we only got to problem D, and none of us solved D. I think my opponent was really closer than I was. I was like also fairly close, but yeah, we only got through 3 problems.
I see. But in my round, I got destroyed. So we got through. Well, he got through 4 of them. I got through A and B.
Oh, you had a really tough opponent, right? Yeah, you basically like solved the same number as I did, but then your opponent just like solved more.
Yeah, I know. I don't know. I don't know lucky, but
It's actually kind of it's quite intense because you have to try and work out how many how many assumptions to make and like how much. Sometimes, I mean, I don't know how it is for you, but occasionally I just like I'm not used to just making assumptions and sticking to them if I don't have a proof. But like occasionally now I was like I missed something in problem E. I had a bug in the end. I just submitted last second, and I had like a conceptual bug about like parity basically.
yeah, no, I do the same. I also definitely don't read very carefully. I think I misread D and E at least once. So my first submissions are kind of nonsense. But... Well, for D, my first one was actually very close to the intended. In my binary search, I kept like influencing the actual array, and then I forgot to undo it. But yeah. Okay, yeah, you can see a whiteboard.
Okay. All right. Looks like this setup works. I guess I also need the problem. What was the first problem?
It was about like a clock.
Oh, right. The first problem was a clock. Yeah. So I don't think I drew anything for the first problem. Oh, this is this is something else.
I see. Is that problem C?
Oh, I think this is cat theory. This is problem C.
Oh, right. I see.
That wasn't now. I wasn't doing that now. So yeah, problem A was like you're given.
Oh, okay. No, I can't see that.
Wait, you can't see this?
I can see a grid.
Oh. Wait, what? Oh, I shared the wrong screen. I've got like 2. Wait, can I not share that? Oh, this is it. I think. That's really weird. You can't see the screen.
Well, I can see no stream, so I can just look at that.
Okay. Because there's like 2. Remarkable has this like double tab thing. So there are 2 tabs, but you can only see like.
Yeah, I can see that one with the grids on it.
Yeah, I'll just share my entire screen then. I think that works.
Okay, yeah, sure.
Bit of inception going on, but maybe I can hide this.
Okay.
Yeah. Can you see like the clock?
Yeah, I can see it. I can see it.
Digital clock. Okay.
Very good drawing.
Yeah. So thank you. So this was the first problem. We just got like a string like this, and we had to find the next palindrome. I mean, that was just like you brute forced that, right?
Yeah. I just iterated until it was a palindrome.
Just like keep going until it's a palindrome. You could probably like construct it somehow, but that's just really not fun.
Yeah, no, I don't want to do that.
You could find like the longest prefix that you could keep, and then let's not do that. Okay,
Yeah,
let's go to the second one.
I guess we should check the next hour. Or like, yeah, okay. I mean,
Oh yeah, I mean if
like until the next hour is like doesn't end at 7, 8, or 9. And the current hour.
you mean there will always be a palindrome, but within every hour. Oh, there won't be. Wait, there won't be one between like
Yeah. So you have to check
16.
the current one, I guess. Yeah. So if you check the doesn't end with 6, 7, 8, or 9, that is, and the well, I guess it can end with 6 and 0.
Oh yeah, 0660. Yeah, I guess at this point we're just like hard coding it, but yeah, you can.
Yeah. I don't think there's much thinking to be done.
Yeah. All right. Next one, I guess. The second one was something about permutation, right?
It was like you're given some numbers and you have to find the largest subset with whether max minus min is less than 5 or not more than 5.
Oh, right. Yeah. Yeah, like sort it in 2 pointers.
Oh, I just made a map of them all and then like iterated. Like I went through it once to make the map, but then just checked above 5, like from AI to AI plus 5.
Oh, you had like a frequency map,
Yeah.
total frequency, like in the prefix.
Not even in the prefix. I just like I went through it once to build a map, and then went through it again.
So you had a map saying like I have what was your map for?
It was just a count of each number.
Okay, yeah. Okay, so you had it was like 1 1, 1 2, 2 3s,
Yeah.
a 4 and a 7. And then for each one you'd say I've got one of these. Oh, and then you just
I just looked forward 5.
ah. Yeah, actually since they're only it's only 5. That makes sense. I just read 5 as like some constant for some reason. Yeah, that makes sense. So you just
Well,
like
I wrote 4 by accident and then didn't get it in time
oh, that's unlucky.
because I said strictly less than 5.
Yeah, that makes sense. I mean I did it like differently, but basically the same. I just like sorted all the numbers and used 2 pointers to keep track of like where
Yeah, that makes sense.
what the biggest range was. But yeah, I think yours was probably nicer to
More brain dead. Yeah.
I mean, usually the more brain dead solutions are the ones you need to go for.
Yeah, that's what you wanted. Let's say it. Or just in CP, to be honest.
Yeah. Just in CP in general.
Yeah. Minimize thinking.
Minimize thinking. I mean, yeah, you do that sometimes, but sometimes I can't make myself do that. Like there are some cases where, for example, if there's a case where like, I need to set some constant to like to some value that's like very like I have some like min value and I need to assign it to something very big and then I'll keep taking like mins with it and something else and assigning it back.
Sure.
Usually like if the maximum possible value this could be is like 10 to the 5 or something, you could write like 10 to the 5 plus like 7 or something and just be, just add some kind of constant there.
Yeah.
Or if it's like n, you can say like n plus 10 and you'll be fine.
Yep.
But for some reason, like I can't bring myself to do that. I always like work out what the smallest possible values I could use is. So it's like principled or something,
Yeah, that's interesting. I've never heard that. Well, did you, for binary search, do you like make sure the bounds are optimal as well?
Um. Oh, in this case, I didn't use optimal bounds. Like, I mean,
Okay.
there are two binary searches here. In this last problem, you have to kind of have optimal bounds in the sense that like
Oh yeah.
it's
Yeah.
just a binary search and all possible answers mean something. But in one of the earlier ones where it was just like a bigger binary search, then I just did like 10 to the 15 or something.
Okay. Yeah. Well, I did 10 to the 9 plus like 10.
Yeah,
But 10 to the 9 should be optimal.
yeah. Oh, well, actually, wait. I think I did 10 to the 9 plus 1.
Okay.
I think I actually did 10 to the 9 plus 1. I changed it from 15. Which problem was this? Yeah, I did 10 to the 9 plus
8.
1.
I see. Yeah.
I also didn't finish this because you beat me.
Oh, okay. Well.
Maybe it's because I was thinking about this too long.
Yeah. Makes sense.
Yeah, okay, we've talked about B. What was C? That was
The
permutation.
gorilla one.
Oh, that was the gorilla. Okay, I keep. Okay, maybe there's no permutation problem and I'm misremembering. Yeah, the gorilla one, we just had a grid and we had certain values to put in the grid basically. And then our total score was like the sum of all values in all like squares of side length k by k. Um, did you just? What did you do for this?
So the grid is you put the like for each square there's like a number of times it's covered by some subsquare. And you want to put the biggest one in the one that's covered by the most. And like keep going in that fashion. So I kind of just tried to implement it. But it's a little bit non-trivial because you have to I just read the constraint n times n less than 2 times 10 to the 5. That would have been nice to know.
Yeah.
That makes it so much easier, actually.
Yeah. Oh, so you didn't use that?
No, I was trying to code it without that.
I was planning to do it without that as well, but then I saw it. So yeah, I just took all the, I just iterated through all this possible cells and like calculated how many k by k squares covered it. So like for this cell it would be 2.
Yeah,
for this cell it would be 4. Pushed those all into a list, into an array, and like sorted that array and the height array as well, and just like multiplied them pairwise from the biggest.
Yeah, makes sense. I guess like the dot product or something.
But did you you started from the middle of the grid and like started moving out like this or something?
Yeah. Well, I mean, I tried to calculate like the number of cells which would be maximal, and then when I run out, I would try and figure out like how much I need to shrink it by. Because like the number of maximal cells like forms a square itself. Well, I guess a rectangle. And then when you decrease a dimension, is basically just decreasing or increasing the dimension of the available space. I don't know if that makes any sense, but
Wait, can you say that again?
So like the number of cells that are covered by the maximum number of subsquares, it forms some rectangle.
Oh yeah, if you like with like k minus 1 cut off from the outside of the whole.
Yeah. And then if I cut off like one more from the ends, that's like the next optimal thing, the next optimal shape.
Yeah, but then so if you look at this, wait, give me 1 second. So if you've got this being the whole, what is this color? If you've got this being the whole grid, you're saying, let's say if k was, if K was 3, like this, all the cells that are in like the maximal number of squares of length K by K, like for example, this one is in this one, this one, this one, it's in like 9 of them, right? So,
Yeah.
so these are all the cells that are in there.
Yep.
And then, so these are obviously the best cells. So you want to fill these first with the biggest numbers, like you said. And then, are you saying this layer is now the next best set of cells?
I mean, not quite. It's like the next, but the next. So I don't think the corners are the same.
Because these will be
Everything
different
else.
from these. I think.
Yeah, but yeah.
Okay. Yeah, makes sense. It's just I don't know how you implemented this faster than me. If you like didn't realize
I
the
didn't.
intent.
I didn't. My implementation won't be correct. But,
Oh, I got this one first.
uh,
Did I get
Yeah,
this one first? Okay,
yeah,
I got this one first. All right. Yeah, fair enough. I was wondering how you did this so quickly, but yeah, that constraint I guess was like just made things easier. But
yeah, this is why I shouldn't read the problem more.
yeah, oh man, same thing happened to me in my actual round in for problem C there as well. Like one of the constraints just cooked me. I was looking at it for like 10 minutes and then I realized it was a 2-minute problem.
I see. Right.
Yeah. Okay. So that was C. We just do the thing I said basically, or this could also work, but it's longer.
Yeah, no, I wouldn't recommend doing that. Read the problem, I guess.
Yeah. Yeah. That advice seems to be universally beneficial. Okay, so finally we're getting to the wait, what was D? I didn't implement enough of it to be able to tell what it was. Oh right, yeah.
So you have an array and you can you have to decrease an element like 3 times and then increase the previous one once and the one before that twice.
Yeah, so you've got this array, and you're going through all of these positions after the first 2, and you can do this operation where you say, for example, you move 1 to this side, but you have to move double that, so 2 to this side, or you can do like 2 and 4, 3 and 6, whatever. And you want to maximize the smallest value left in the array. So you want to like balance the values out. I think that the tricky part, the way I looked at this was, it felt like if it was plus D for both, then it would be easy, in a sense, because you could like binary search the answer, and then if you're saying the value you need to get to is like 12, for example, the current value. If the first value in your array is 1, then you need to add at least 11 on move 1 to get this one up to a 12. And then oh wait, no, never mind. Even if the D's were the same, I think this still doesn't work. Because like if you have a
I'm not sure how.
If you have a lower value after it, basically. So I was trying at some point to demonstrate that the first move I have to make, it always like makes sense just to lift the first value up to where I'm trying to go and ignore the second value, but that's wrong, basically. So I won't go into that, but it's just, how did you do this? Because I feel like I know how you did it.
Well, the first thing I did was misread it and think that you can make the operation in any order. So I thought you could start with the last element, which makes it kind of easy, because you can just binary search and do a greedy.
Yeah.
But
you can do that anyway, right? Just like as in that's I think exactly what you said, except is the words that I would have said for how to solve the problem.
Yeah.
You have to start with the last element, but then
Yeah, yeah.
like you don't actually start with it. You just start thinking about it first.
Yeah. So you do the last element, and you just have to make sure you don't like decrease it more than the initial value.
Yeah. So if did you also binary search?
Yeah.
Yeah. So if this problem's kind of hard to solve, but if you just want to check whether like you can get at least 4 as your answer, then, or let's say at least 3, then like the last value, you might as well just decrease it on the last move. You might as well just decrease it as low as 3 or as close as you can to help out the earlier ones. And then that means you're moving 1 here and 2 here. Back to this one, you do the same, and you know that now since you've got a +1 incoming onto this cell, then you can afford to decrease it down to 2. I think. Is that right?
Which one?
Oh,
Yeah. Okay. I know what you mean. Yeah.
like the one directly before it, you can afford to decrease it down to 2 because it'll get a +1 afterwards.
I was thinking more like you you do it in reverse order, but you make sure that you don't do too many operations on that element. Like you can't decrease it more than its initial value.
Oh, right, yeah, sure. That makes sense as well. Yeah, you can just
like misreading it and implementing the wrong thing it was very close. So it probably helped me come up with the solution, to be honest.
Yeah, that's kind of weird because like I was sitting there for a long time thinking, and then like as soon as I realized backwards, I think backwards was like the main realization. I guess you thought it was backwards, but for the wrong problem. So
yeah,
it's kind of funny.
And then I kept filling the samples. I was really confused. And then I realized that my understanding must be wrong because I was definitely outputting the right thing. So
yeah. Okay, so that's the last one we solved. Do you want to move to E?
Sure, yeah.
So I also saw you were submitting this. I think I basically had this, except for like the line that I missed, basically.
Oh, that's rough. I was not very close to finishing implementing. Well, I guess like a few more minutes maybe. But...
Yeah, honestly, I mean, it was a pretty key point that I missed though. Like it was like kind of a key case.
Okay.
So wait, this was the robot problem with strings, right?
Yep.
So we have like a sequence of moves. Up, down is kind of stupid. So up, right, up, right, down. Say so this starts at like 0, 0, and then goes up, right, up, right, up, right, down. So it ends here, and we want to make it end somewhere else. So let's say if we want to make it end here, what's like the shortest segment that we have to change, right?
Yep.
Yeah. Do you want to start talking, or should I start talking? Up to you.
Sure. So, I mean, I think I just binary search for each like left point, like what's the first right point, which will let you like move change the path enough to get to the point. And I basically just stored a prefix sum of like all the U's and then R's and D's and L's to like calculate how many in like some given substring, how many R's I have, L's and D's and U's. And then I was going to do some greedy where like if I want to go like want to go down, I first want to change U's to D's. And if I want to go left, I want to change R's to L's. And then after doing that, change the, like maybe I'll have some L's left over, which I can use to go up or something. But yeah, I didn't have time to implement everything.
Yeah, I see. Like the main idea is the same for me, but I think I was just implementing it a bit differently. So like still like binary searching for each start point. What's the shortest range I have to change to make it correct? But the key, well, not the key. The thing I was doing was like for each one. Again, I've also got like for each prefix and for each suffix. I mean, just for each prefix, but you can take differences. What's like the total like movement in X and the total movement in Y.
Yep.
And so I kind of know that if in the binary search, like let's say I'm now considering this range, then everything before and after, I can add up the total movements. And now I know like if I just took this middle range out, then I'll end up like here, let's say. Or wait, no, I'm just taking 2 rights out. So I'll end up here.
Yeah, sure. Okay, I guess that makes sense. Yeah, then you can just move towards it. Which is much easier.
And I mean, I think all you had to output was the answer. So I'm just taking like whether the dx, the difference, like the absolute difference, the Manhattan distance between these 2 points is less than 2, which is like the size of the range.
Yeah, I guess so. Yeah, that makes sense. I guess you also have to check the parity.
Yeah, exactly. That's the thing I missed. Like if the parity's off, you not only like will you not be able to do this, but you just like can't get there at all.
Yeah. No, that's definitely cleaner than what I was gonna do. I don't know why I didn't consider that. But...
It seems like if you put 2 programmers and give them a task, it's much more likely that one of them will find a faster solution than just one.
Yeah, I guess that makes sense. I don't know.
Yeah, I don't know.
I also read this one wrong as well, so I had some other bullshit before. But
this speed-based reformat is really intense. It's quite fun in my opinion. What do you think?
Yeah, no, it's really fun. I mean, I wish they could implement it in a more like permanent way, but I don't know how that would. I think we would run out of problems very quickly. So I really like it. But it's definitely fun.
Yeah, I mean, it's like, the problem if you want to practice with like easier problems. I mean, maybe it gives you a bad habit for contests just because it's getting me more comfortable with submitting without thinking.
Yeah. And I think on my actual match, I was reading too much, so I tried to read less, but it didn't work out.
Yeah, I see. Yeah, I think you got an unlucky pairing in round 1, actually. From what I saw.
Yeah, no. I mean, he almost beat Geotherm after, so that's hard win. But I don't really know. I mean, I didn't think I was going to win that one, to be honest.
Yeah. I also signed up for the fun mainly. Like GM.
I didn't think I
get tournaments. That's quite fun.
Round of 16 of them.
Yeah. All right. Cool. I mean, I'm streaming this. I think people are watching. For anyone watching that doesn't know, I basically I started the stream, and I think the first thing that happened on the stream was like the screen said like 7 seconds to go or something. Or I think it said Yeah, 7 seconds to go, and then a refresh, and it said contest is running. So I didn't really have a chance to like explain what was going on. I did it in like the break after problem A. But yeah, so I'm facing Will as a Will, aka Intelligent, as fun like practice round between friends. We both go to the same university. We're both at Cambridge studying computer science, and we also like did a London competition together. Well, we are perennial teammates, it seems. So we've been teammates for 2 years.
Yeah.
3 men in a boat. That's us. Well, our third man isn't here, but maybe we should have got him to commentate. Actually,
True. Yeah. Wonder
next time we can do this again. This is a fun format. It'd be cool if they released it to
Yeah.
to people. At the
I
moment,
don't really know how. I think we run out of problems pretty quickly. Well, no, I think like I think a lot of people would grind it a lot, and then they would quickly run out of problems.
oh, just like 1,000 and 1,200 problems.
Yeah, I mean, I like already like when I'm facing some people, like they've solved so many problems that they become so old that it's kind of hard to do anything.
Really? Oh, yeah. I didn't think about that. I kind of just assumed that there were enough problems. Because
Yeah,
I feel like
they're unpractical.
I feel like maybe GMs and IGMs wouldn't really grind 1,200 problems as much, but
Well, I guess there's a lot of like really old people who have done so many contests that
oh yeah, maybe.
like that old, but they've been doing CF for a long time.
Yeah, he's pretty experienced. All right, cool. Well, that was pretty fun. Thanks for agreeing to do that on such short notice.
I know it's okay. It was fun.
Yeah. See you in lectures? Question mark.
Maybe. Anyway.
Maybe. Yeah. Okay.
All right.
Have a nice weekend.
Yeah, you too. You're right. Bye.
See you. All right. That's the end of the stream. We'll end it there. So yeah, that was pretty fun. Tune in tomorrow for my game, for my matchup in round 2. Yeah, I'll put the stream out. I'll schedule the stream in a minute so you can actually see when it is. But yeah, see you in round 2.